areas we are looking into improving going forward. So quickly, overview about Apache Flink. Flink is open source distributed stream processing engine that can handle stateful and stateless computation over bounded and unbounded data. And this is why we see high adoption in Bloomberg. It unifies workloads that otherwise need separate systems. It's designed for high performance and fault tolerance. This makes it a good framework for business critical applications that require very low latencies. On top of that, Flink provides a rich set of features that support real-time data processing. So events can be processed the moment they occur, real-time ETL, which lets you transform and move data without any scheduled batches. Event-driven application, which lets your application react to signals in data. And finally, analytics and monitoring at scale, letting teams understand trends and patterns as they occur. So in short, Flink is not just about moving data, it's about enabling complex, stateful, and reliable processes in real time. At Bloomberg, we run thousands of Flink applications deployed across multiple Kubernetes clusters spanning several tiers. These are use cases that power critical workloads that are crucial for Bloomberg's core financial products. Some of them give market insight data for traders, analysts, other financial professionals across the world. And because these applications are near real time, any kind of downtime is not accepted. It can range from anything between financial loss to misalerts. So reliability is a hard requirement, it's not an option. So jobs must keep running, state must be preserved, and recovery should be fast and correct. So that's the requirement at Bloomberg. So in order to build this kind of a resilient, self-healing, and highly available infrastructure, we adopted Flink's official Kubernetes operator. This is an open source project that is maintained under the Apache Flink community. It's designed to simplify managing Flink jobs on Kubernetes. It does so by treating Flink jobs as first-class citizens in Kubernetes cluster. And this works well for our infrastructure because, hey, under the hood, everything is a Kubernetes cluster. So that was a good move. And then job lifecycle management is just half the story. In order to run Flink jobs reliably in production, we needed fault tolerance. And that's where Flink's internal checkpointing mechanism comes in. It is how Flink protects its internal state from pod crashes and node fails. So checkpoint, we can think of it as a distributed snapshot of operator state and the input offset. How it works is the checkpoint barriers are injected at regular intervals into the input data stream, and these barriers flow through the job graph and request every operator to record its state. Simultaneously, the data source connector records its input offset to know which records are being processed at that point of time. All this data is written asynchronously to an external source like S3 or HDFS, so that when a failure occurs, the Flink job knows exactly what is being processed and how it is being processed. Checkpoints protects the Flink job from node crashes where the node is hosting task managers or job managers. Task manager crashes are fine, but if a job manager fails, the recovery time takes longer. And to reduce this, we can configure the job manager HA. We can do this either by Kubernetes HA or Apache Zookeeper. The idea here is simple. At any given point of time, there are multiple job managers running. Only one is elected as the leader. The leader job manager continuously coordinates the application, whereas the standby job manager continuously tracks the state, so that in the event that the leader job manager crashes, the standby job manager takes over instantly, and the job is recovered with minimal downtime. While this is great for in-cluster failover, it still doesn't protect you from a full cluster failover. So the big question here is what happens if the entire cluster goes down? Either checkpoint or job manager HA cannot protect you from that. But then you can ask, does this even happen? Yes, cluster level outages, even though they don't happen every day, you should be ready for them. They can happen for a number of reasons. They're listed in this slide. Some of them are infrastructure blips or human mistakes, like think of a misapplied kubectl command that can wipe out an entire namespace in a cluster, or control plane issues where the API server crashes or a certificate expires, leaving the entire cluster unmanageable. So the key takeaway here is Flink provides a strong in-cluster fault tolerance, but we had to design our infrastructure for cluster level failover resiliency as well. Until now, without us doing anything, we have seen some approaches adopted by our tenants on our platform. The first one is the active-passive setup. The idea is that if the active cluster goes down, someone manually uses the last successful checkpoint to start the job in a standby cluster. This is a great way to recover the job because it ensures all the exactly once guarantees, the ordering guarantees, and there is absolutely no data loss during recovery. So it's great for a stateful computation, but it comes with a limitation that it requires a manual intervention to happen. And also the recovery time depends on how large the state size is. So while this method gives a strong correctness guarantees, it does so by the cost of lower recovery. And then we saw certain active setups that our tenants have embraced. The idea here is that there are two Flink jobs, identical Flink jobs running side by side on separate clusters. They are continuously reading from the same data source, and a coordinator service like Apache Zookeeper here elects one of the Flink job as the leader. Only the output of the leader Flink job is promoted downstream. The other Flink job, the standby Flink job's output is discarded. So what happens here is that the key benefit over here is that there is minimal downtime, and it makes it appealing for applications that have tight SLAs. But it comes up with important trade-offs, since both the jobs are running independently of each other in separate clusters, there is a risk of data loss or duplication in data processing when the failover switch happens. Doing so, we lose the exactly once delivery guarantee that Flink promises. Not only that, the application's internal state can diverge at some point of time. So during a failover, we end up with inconsistent application states. So it comes with these problems. We have also seen a different variation of this active-active setup, where both the Flink jobs are continuously producing output. Instead of discarding them, we run it through a caching layer. The idea is that if two identical events are seen, only the first one goes through. This is again good because it minimizes the downtime because both the applications are running always, but there are some serious caveats here. The dedupe caching layer acts as a very critical dependency that we have introduced in our system. And then there is no ordering guarantees that the Flink promises. The syncs have to be idempotent or else inconsistencies will flow through the application. So while both these designs give us near instant failovers, they do so by sacrificing important guarantees. It's a pragmatic solution for maybe stateless application, but it's not good for stateful pipelines. Mihaj, you want to summarize it?
Yeah. Good. Cool. So as Iha has gone over, there are several strategies that our users can sort of implement to have job recovery on a cross-cluster level. However, as our platform started to grow, we run into other types of issues of scale. First off, currently control planes are still tied to a single cluster. So given our infrastructure spans multiple tiers in multiple environments, users would have to manage a bunch of different kube configs. And as the number of jobs grows, this starts to become quite cumbersome. You have to keep track of which clusters you're deploying to. Clusters can have different amounts of available resources, so it's just things that users don't really want to think about. Additionally, Flink deployments, Flink applications are going to be long-running jobs. And as a result, the nature of long-running jobs means that jobs aren't just eventually going to fail, they will eventually fail. And as a result, Apache Flink needs to have a way for this job to recover. Luckily, Apache Flink does provide built-in high availability support, but this high availability, as Neha has mentioned, assumes that the recovery is going to take place in the same cluster. And finally, that means that cluster failover is a manual process at the present. So if a cluster goes down, we get alerted of this, and tenants will have to manually failover their job if they're using an active passive setup. And this can become quite operationally expensive and error-prone. And so given these limitations, we started to think about an ideal landscape where you just have a single control plane that users could apply and manage their jobs to. And so we wanted this unified control plane, which would require users to just have a single kube config. They could deploy their jobs to a single place, and they could use the Kubernetes API as is. Furthermore, once applied to the control plane, we wanted this control plane to be able to intelligently schedule these applications to clusters with sufficient resources. And then finally, the control plane should be continuously monitoring the health of the clusters, but also the individual applications that have been scheduled. And in the event that either the cluster or the application is in an unhealthy state, we want those applications to reschedule automatically to another cluster. So as we started to solidify this ideal central control plane, we started to research potential options in the open source community. And that's how we were introduced to the Karmada project. So Karmada, for those unfamiliar, is an open source Kubernetes management system. It helps us as platform owners manage different types of Kubernetes clusters, but also users manage their cloud native applications in a multi-cluster setup. And it comes with a lot of really helpful features. It allows us as platform owners to manage clusters, but also manage the way that users are deploying their applications. It provides users with a unified endpoint for managing their jobs, as well as a unified authentication. And then finally, what this talk is primarily going to be about is the automated cross-cluster application failover. So before we get into, I guess, the finer details of failover, I wanted to go over how Karmada is able to monitor the health of both applications and clusters. Sort of happens in similar but analogous ways. For cluster health, the way that Karmada does this is it's constantly going to be pinging the Kubernetes API health endpoint on each member cluster. And if that endpoint returns 200, meaning that all the components are in a healthy state, things will be as is. However, if Karmada is not going to get a good response from the health endpoint, or it's unable to connect, it'll eventually taint that cluster and force an eviction of all the workloads on that cluster. On the application side, things are a bit more granular. It depends on an existing resource interpreter framework provided by Karmada, which allows Karmada to determine the health of the application based on the status that it puts out. And so this was our first phase of using Apache Flink on top of Karmada. So on the left side, you'll be able to see a propagation policy. Propagation policies are CRDs, which are essentially a blueprint telling Karmada what type of resource you're going to be scheduling, and then also how you want to schedule it. So in our case, we, for instance, set some spread constraints. We wanted the CRD to only get scheduled on a single cluster, and so we set the max and min cluster state equal to 1. In this case, we were able to deploy our Flink deployment to the Karmada API server. Karmada will decide where to schedule it based on available resources. And then once the Flink operator brings up the Flink deployment, it'll report its status to the Karmada API server, and users can ping that API server to get the status of their application. I'll hand it back to you.
So now let's talk about some of the limitations we have faced when we first onboarded Karmada. Firstly, Karmada needs to know when to fail over the Flink application. With the default settings, Karmada has no idea whether Flink is healthily running or not. The second thing is, during a failover, like we discussed before, the Flink has to start from the last successful checkpoint. For this, it has to have that information of previous state to resume from. Again, with the default setting, Karmada has no idea how to start the Flink application. So before we could design a solution for this, we had to understand how to interpret the Flink's internal job state machine. So this is a very uncomplex way of representing the Flink's job machine. It's much more complex if you see the official docs. So firstly, if the job is in either running state or any of the terminal states, Karmada can interpret this as a healthy state and ignore the Flink's health. It can just leave it as it is. Then if the job state is in one of these ephemeral states, then Karmada needs to understand why it reached these ephemeral state, and only based on that it should do the failover. Finally, these are short-lived states that are part of normal transition, so Karmada can ignore them because they will finally reach a terminal state, and those terminal state we have decided is a healthy interpretation. Here's an example of a healthy state transition. First is the reconciling state, where the job manager or any other component has not been scheduled or hasn't reported any status yet. Then we go to the initializing state, where Flink components are starting up. Then we reach the created state, which means that the cluster is ready to process data. It hasn't started processing, but it's ready to start. And finally, it enters the running state, where it started processing the data. Now, if the state has moved from running state to created state, it means that something bad has happened internally, like a job manager has crashed or some other cluster level internal issues has occurred. So this is an example of an unhealthy state transition, and this is when Karmada has to look at what caused this kind of unhealthy state transition. Like I mentioned before, just because the application is in one of the ephemeral state, it doesn't mean that Karmada blindly fails over the application to a new cluster. It needs to understand why it went into that error state. It can go because of many reasons, like a misconfiguration, like it's a bad container image, or there are runtime problems, like a bad upgrade has happened. So just by failing over these kind of applications will not fix these problems, so Karmada should ignore them. And then this is how an error message is populated in the Flink CRD. This is an example for bad image error. And then this is how Mihash earlier demonstrated. This is how we integrate Karmada into our platform. And to deal with the first limitation, we have included a field over here in this CRD that indicates why the application has gone into one of the ephemeral state. So if the deployment becomes unhealthy, the Karmada will wait for a threshold time and then purge it right away to reschedule it on a new cluster. So now that Karmada has deemed an application unhealthy and purged it and started it on a new cluster, does this mean that the failover was successful? Not exactly, because once we started like this, the application starts as new. We never provided it the previous state information so that it can continue processing from where it left off before the failure happened. And I think Mihash will go over that.
So obviously, if a failover happens and your job starts as new, that's the problem. And so the issue here was that although Karmada was interpreting the resource correctly and failing over the job to a different cluster, in order for the operator to start it from a specified state, you need to set an initial state point path. Now, this currently was not something that was supported, and so we needed some sort of pointer that would allow Karmada to inject state into the application as it's getting failed over between clusters. And so after working with the community, we came up with the idea of state preservation. This is an enhancement that extends the existing failover API, and it comes with 2 new fields. The first of which is just a JSON path. So this is just an expression that identifies a specific piece of data that you'd like to get fetched from the application status. And then an alias label name, which is just the name of the label. You can set it to whatever you like. So for us, we set it to be equal to the job status.job ID, as the job ID is integral to setting the checkpoint path for applications. Now finally, although Karmada is now able to package this job ID into the Flink deployment manifest, we still actually have to consume the job ID. And to do this, we rely on Kubernetes, which is another open source project. For those unfamiliar, it's an open source policy engine. So it allows users to set various validation or mutation cluster policies, which can affect resources that are deployed on Kubernetes. So in our case, we introduced a rather small mutation policy that searches for the presence of this failover job ID label. It will then call an external API, fetch the latest checkpoint associated with the job ID, and set the initial save point path for the Flink deployment. So by enforcing this initial save point path, we instruct the Flink operator to start the Flink application from its previous state, having a graceful restart. So here's just the labeling. So we inject the initial save point path there. And so this is sort of like a finalized diagram of how the failover is happening with the new state injection. So let's assume we have a job running on one cluster. All of a sudden, let's say half the cluster's nodes go down for some reason, and the job is stuck in a reconciling state because there aren't enough resources to reschedule that pod. In that case, after the toleration seconds is elapsed, Karmada will actually reschedule that application. It'll immediately purge it from that cluster. It'll re-inject the job ID as a label into the Flink deployment. And once it's reapplied to a new cluster, Kubernetes will be able to automatically inject the latest save point path for that application, from which point the operator will be able to restart the application from its latest state. And so what have we noticed using this feature in practice? First off, I want to make it clear that application failover across clusters really should be a last resort. Although automated failover is incredibly helpful, we prefer relying first on the Apache Flink built-in high availability mechanisms to recover the job as a first step. If Apache Flink is unable to self-recover within a certain amount of time, then failover does become a very convenient option. And this is particularly helpful when users maybe have slightly more relaxed downtime requirements. But also it allows us as platform owners and the users of the application to not have to manually intervene outside business hours. Obviously, it's inconvenient to be pinged outside business hours, but also like if you have a lot of jobs that are impacted, this can quickly become quite error-prone. And so what are the key limitations here? The first is application failover is still going to be bound by the startup time of the application. So the problem here is we can't set the toleration seconds to be lower than it takes for the application to get to a running state. Otherwise, Karmada is never going to treat the application as healthy. It's just going to keep bouncing between clusters, and that's not helpful. Now, we are working on improving this, but additionally, even if we were able to fail over this job from one cluster to the next almost instantly, your job is still going to take time to come up. So in a production scenario, you're still dealing with that amount of downtime, the amount of time that it takes for your application to come back up and start processing data again. And in cases where you have a very tight SLA, this is still not going to be acceptable in prod. And so what we found is the real solution is using some of the built-in strategies that Neha has talked about, such as active-active, in conjunction with using cluster health monitoring and failover. So recently in Karmada, as part of the 1.14 release, we introduced a new resource called a cluster taint policy. So this allows admins to define rules for applying and removing taints from clusters based on specific conditions. So in our case, we have this queue components healthy condition. In the case that this queue condition is missing from the cluster manifest, the cluster taint policy controller will actually add in a no execute taint, And what this allows is it gives finer granularity for users to be able to determine when their application should fail over in response to cluster outages. What I mean by that is, let's say, for instance, the cluster is in an unhealthy state. We take out this condition saying that kube components are healthy. Karmada will automatically set the taint on that cluster with a no execute label. And as a result, each propagation policy that's controlling these workloads is going to have a taint toleration built in. And this taint toleration can be set to whatever the user wants their SLA to be. So it allows them to be hypersensitive to these types of specific cluster outages depending on their use case. And that can be very helpful. So lastly, just going over some of the key benefits here. As we mentioned earlier, one of the biggest pain points, just from an operational point of view, was needing to manage a bunch of different kube configs. By having a centralized cluster, we're able to just manage, deploy jobs from a single place. And then secondly, obviously what's a huge benefit for us was the automation of cross-cluster failover. And this is critical to ensuring data pipeline resiliency. So again, I wanted to stress, cross-cluster failover should be a rare occurrence, but things can happen that cause the clusters to get into an unhealthy state. And in those cases, you need to be ready. So in those cases, it saves us time. It allows us as platform owners, but also users' applications to auto-recover without our explicit involvement. Now, following that vein, different users can have different failover requirements. So some may want to be more sensitive to failover, and this is configurable via the taint tolerations, which I mentioned earlier. But as a whole, automated failover has really helped remove a lot of the operational burden that comes with maintaining our infrastructure platform on a day-to-day basis. And similarly, maintenance windows no longer require heavy coordination, as failover provide us with necessary DR testing. And then lastly, wanted to talk about how involved we've been with the Karmada community. We're constantly improving the platform. In the next release, we'll be adding some support for workload anti-affinity, which will be particularly useful for active-active use cases, which Nina had been talking about, essentially making sure that active applications are never scheduled to the same cluster, as if they were and a cluster went down, you're going to have a problem. But yeah, these are currently in the works, and if you're interested